right. I want to address y'all as, hey, all you cool cats and kittens. But I'm afraid that some of you might not get it. I address my organic students like that, and they seem to not have gotten it. All right, so I have so many computer screens open. We're on part 3 of chapter 16. I really hope that it doesn't take me 45 minutes for every single page because there's like 20 something pages. Maybe not, maybe 10. Okay. So, I hope everybody's doing well. I noticed in my chapter 15 videos, I had a different color pair of tassel earrings on every time. Look, I got a new color. I also have on a funny shirt. So, I'm trying to find humor where I can. All right, maybe if, I don't do all this side chatting, it won't take forever. All right, so let's flip back. I don't know what my hair's doing. To our chapter 16 notes. Let me get them pulled up for you. Might have to go to the whiteboard on this, not, okay. Why does it look so little? Okay, I haven't done this in a week, and I feel like I've almost forgotten what I'm even doing. So give me a second. No. So we went over the difference between a weak and a strong acid and a base. Okay, so now how do we classify an acid strength? So I'm gonna do it with my picture so y'all don't get sidetracked. Well, we use something called a Ka and a Kb. So here in equation 1 and 2, it's written as an equilibrium equation. So you see the equilibrium arrows right here. So we are going to classify an acid strength by its basically its equilibrium constant. We're just going to represent it as Ka. So that's going to be a equilibrium constant for an acid, and a Kb, so an equilibrium constant for a base. The next bullet here says the farther the equilibrium position lies towards the products, the stronger the acid or the base. In other words, the closer your Ka or your Kb is to 1, the stronger the acid. So you can see here HClO2, Ka is 1.1 times 10 to the negative 2, whereas HCN is 4.9 times 10 to the negative 10. That means that HClO2 is a stronger acid because its Ka is larger or it's closer to 1. So the larger the Ka, the stronger the acid, the larger the Kb, the stronger the base. These will only be for weak acids because strong acids go to completion. So there is no K associated with them. So strong acids or bases, we use one arrow, so there's no K. So no Ka. Same applies for bases. Okay, so the equilibrium constant for these reactions, we actually call them the acid ionization constant because it tells us how much that acid is breaking down into its ions. And the base ionization constant we call Kb. So the tables, a Ka and a Kb table are in your book. The Ka table is on page 695. So 6, I did pull it up. Let me see. I really need to learn to write, don't I? And the Kb table is 711. Let me see if I can pull them up. JPEG, this is what I want. So is this showing? I don't think it is. Let me go here. So here is the acid ionization constant chart. So you will always be given these values on a quiz or a test. When you're doing mastering work, like your post-lecture or something, you'll probably have to pull it up in your book. But you don't have to remember these, they will be given. So anything on this chart is a weak acid because, again, only weak acid have Kas, and there are your Ka values. There's also the pKa values, which we'll get to in a little bit. All right, so we're going to use these numbers when we start working problems, but I just wanted to show y'all that real quick. And there's also a KB table. Okay, I got too much going on here. Oh, okay. Back to this. All right, so let's keep scrolling. The next part says auto-ionization of water. All right, so I mentioned earlier that water is amphoteric, meaning it can act as an acid or a base. So, let's see now. Here shows you the auto-ionization of water. We have two molecules of water. One's going to act as an acid, one's going to act as a base. So in other words, we're going to form the hydronium ion and the hydroxide ion. Of course, since these two are the same, we could simplify this equation to this. Remember, hydronium and the H+ ion we'll use interchangeably. All right, so remember in your K values that we only include gases and aqueous liquids, okay? So H2O is a pure liquid. So we do not include it in our Ka expression. So the K for water then, for this equation, let me clear this up. I'll do this instead. All right, let's try this because it lets me erase. All right, so if I wanted to write the Kc expression, all right, whatever. All right, Kc for this equation would just be, you can either write it as H3O plus or H plus. It means the same thing. So I'm just going to do H plus. OH minus. We always do products. What just happened? Y'all. Okay, y'all get my point. Because it's always products over reactants. Well, my reactant is a pure liquid, so I don't include it in this expression. So we could actually rename this as the KW because it's for pure liquid water. And so that's just H plus OH minus. Well, at 25 degrees Celsius, this is equal, the KW is equal to 1 times 10 to the negative 14 at 25 degrees C. Because it's a constant, okay? So I'm giving you that. I didn't just make that up. So, let me take you to the whiteboard. So let me show you how this works. in terms. All right, so if Kw equals 1 times 10 to the negative 14th, and that's equal to the H plus concentration, OH minus concentration. For a neutral solution, your hydrogen ion concentration and your hydroxide ion concentration is equal. So we could say that it's just X times X equals 1 times 10 to the negative 14th. Well, this is X squared. So if I want to find X, I take the square root of both sides, and X would be 1 times 10 to the negative 7th. That would be molarity. That would be our molarity for our hydrogen ion concentration and our hydroxide concentration. So in a minute, I'll show you how that relates to pH. So if your hydrogen ion concentration and your hydroxide ion concentration are equal, you are said to have a neutral solution. This is neutral. And this is what they'd be equal to. Okay. I'm going to erase this. Okay. If my hydroxide concentration was greater than my OH concentration, I'm going to have an acidic solution. And then if my hydrogen ion concentration is less than my hydroxide ion concentration, I'll have a basic solution. And again, if they're equal, it's neutral. So if you flip over to the next page on your notes, I'll take you back. Clear, new share. We go to example 16.2. It says calculate the OH minus concentration and determine if the solution is acidic, basic, or neutral. So in this first example, you're given the hydrogen concentration. It's just written as the hydronium ion concentration. And then this next set of problems, we got part 1. That's supposed to be a 1. There. Then the next set, you're given the hydroxide concentration, asked to find the hydrogen, determine if acidic, basic, or neutral. All right, so all of these, you're going to use that the Kw equals 1 times 10 to the negative 14. Today just might not be my day, guys. All right, Kw 1 times 10 to the negative 14th. All right, so that I have plenty of room to work, I'm going back to the whiteboard. And I'm not going to work all of these because this is a rather simple problem. All right, so for part A in the first one, we have the hydrogen. I'm going to put just hydrogen. It's less for me to try to scribble on the screen. 7.5 times 10 to the negative 5th molarity. All right, so we're going to say Kw equals 1 times 10 to the negative 14th. That is equal to my hydrogen concentration, my OH minus concentration. All right, so I have the hydrogen ion concentration, so plug it in right there. Then we're going to solve for OH. So what that becomes is 1 times 10 to the negative 14th equals 7.5 times 10 to the negative fifth. We'll just abbreviate the OH as X. All right, divide both sides by 7.5 times 10 to the negative fifth. Oh, that's bad. Times 10 to the negative fifth, and that is molarity. All right, so when I divide 1 times 10 to the 14th divided by 7.5 times 10 to the negative fifth, I get my OH minus, concentration to be 1.3 times 10 to the negative 10. If you did not get 10 to the negative 10 as your exponent, then you need to put these into parentheses when you type them in your calculator. All right, so let's compare. Is my OH concentration smaller or larger than my hydrogen ion concentration? So I'm comparing 7.5 times 10 to the negative fifth to 1.3 times 10 to the negative 10. Well, my hydrogen ion concentration is actually larger because it has the smaller negative exponent. So this part A would be acidic. Okay, so instead of working the others, I am going to give you the answers. Okay, let me clear this. Lock this over. No. Okay. All right, so for part 1, and labeled them part 1 and 2, letter B, your OH concentration is 6.7 times 10 to the negative 6. To solve this now, I'm just giving you the answer of it already solved. Therefore, that one is a basic solution. Part 2, in A, you get the hydrogen concentration to be 6.7 times 10 to the negative third, making, negative 13, making that a basic solution as well. And then for part 2, letter B, the hydrogen concentration you get is 1.2 times 10 to the negative fifth, making that an acidic solution. Okay, so those are your answers to example 16.2. I hope you don't have any difficulties with that. It's not hard. You're just substituting your numbers into the KW. KW equals hydrogen plus OH. All right, so let's go back to our notes. Back and forth. All right, new share. Okay, so now let's talk about something else that is common with acids and bases, and that is the pH. So the most convenient way to talk about the measure of acidity is through the pH scale. So how do we get this pH? Well, all you do is you say the negative log of your hydrogen concentration. So the P basically means take the negative log, okay? So this means take the negative log of whatever I have listed here. So negative log of hydrogen concentration. Another way we could express acidity or basicity is pOH. Same thing. The P means take the negative log of your OH concentration. Okay. So when we were talking about the autoionization of water, and I told you that they were equal. No, I didn't write it there. Okay. If I had a neutral solution, both of these concentrations would be 1 times 10 to the negative 7th. I can prove that to you by taking the pH. So here, if I come here, I say the negative log of the hydrogen concentration, which was 1 times 10 to the negative 7th, I get 7. We know that to be a neutral pH. So anything lower than 7 is said to be acidic. Anything greater than 7 is said to be basic, and pH of 7 is neutral. We could also do the same thing with pOH, but pOH, we generally don't report these in terms of, oh yeah, it's acidic because it has a pOH. Yeah, we don't use that a whole lot when we're talking about this stuff, but you will use it in problems. So for pOH, if your pOH is less than 7, it is basic. If your pOH is greater than 7, it's acidic. If it's equal, it is neutral. But again, for me, I'd rather just take my pOH, plug it into this formula, solve my pH, because that's what I'm used to. Okay, so brings us to our next point. pH plus your pOH should always be 14. So if you have your pOH, you want to find pH, just plug it into this formula. Okay, so let's look at example 6.3. Let me try to do this. Okay, without writing like a kindergartner. All right, so 16.3 letter A says calculate the pH of the solution. Is it acidic or basic? All right, well, we have our hydrogen concentration. So I just need to say the negative log 1.8 times 10 to the negative 4. Okay, so if I plug that in my calculator, I'm going to do negative log, not natural log, but log, negative log 1.8 times 10 to the negative 4. I got my pH to be 3.74. So that is less than 7, so it is acidic. Okay, that was easy enough. All right, let me... I wanted to erase this. This is in my way. All right, so for the next one, let me get back to where we were. Y'all. I'll try to do it over here. I don't think I can, but all right. So I want to find the pH. Well, the easiest thing for you to do would be find the pOH, then use this formula and find your pH. So let's do that. So if I want to find my POH, I'm going to take the negative log of my hydroxide concentration. 1.3 times 10 to the negative 2. All right, so I'm going to plug that into my calculator, and when I do, I get my POH to be 1.89. All right, well, I'm asked for pH, not POH. So to find pH would just be 14 minus POH. All I did was rearrange this equation. So my pH then would be 12.11 would be my pH. Therefore, this is greater than 7, so this solution is basic. Okay. Oh. Green. All right, one thing I didn't mention when we were talking up here, but let me erase this mess. Oh, good. Okay. We were talking about finding pH. We didn't talk about what if we have pH and we want to find the concentration of either hydroxide or, trying to clean it up for you, hydroxide or hydrogen, okay? We can do that by doing the inverse of log, which is just 10 raised to the negative pH power. So that's how I'd find my hydrogen concentration. To find my hydroxide concentration, I would say 10 to the negative POH power. Okay, so let's skip back down here to example 16.4. It says calculate the calculate the hydrogen ion concentration for a solution who has a pH of 8.37. All right. Well, then I know to find the hydroxide concentration, it's just going to be 10 raised to the negative 8.37 power. In other words, you're going to push second log. Well, that's what you push on my calculator. Maybe not yours. Negative 8.37. And I got my hydrogen ion concentration to be 4.27 times 10 to the negative 9th. And of course, that's molarity. Okay, so that's how you would take your pH and find a concentration from it. We could do the same thing with POH or a hydroxide concentration if we were given it. All right. I'm going to stop right here and we'll pick up part 4. Maybe I'll learn how to write by then, but don't count on it. See you in a little bit. End.